Alright, so this is the first of two videos on the chain rule for Math 1560, Calculus 1. In this video we're going to go over kind of the basics of the chain rule, what the formula is, where it comes from. We'll do a couple of basic examples, and in the next video we'll do a few more examples with the chain rule. We'll do some of the kind of the basic problems that can be solved once you have the chain rule in hand, and of course we will try to go over as many chain rule problems in class as we have time for. So the chain rule is really, it's the last rule that you need to handle derivatives. The chain rule has to do with function composition. But once you've got the chain rule under your wing, pretty much any function that you can think of writing down, if you can take the derivative, you can figure out how to take the derivative once you've got the chain rule. And I should warn you that the chain rule is probably the one that gives people the most trouble. It's hard to get the hang of the chain rule at first, and so as you're working on it, as you're trying to get the hang of it, it doesn't hurt to break things down into steps. We'll show you in the examples we do later how to kind of break things apart into steps, rather than trying to do it all in one go. If you try to do it too fast too soon, you'll end up making mistakes. But like any of these derivative rules, with enough practice, you can get the hang of things, and you'll find that it's not too bad once you get used to it. Like I said, the chain rule has to do with function composition, right? Anytime you plug one function into another, and one of the skills you're going to need to do the chain rule is to be able to recognize this sort of function composition and figure out what the two component functions are that are being put together to form this composite function. Right? Now, one of the things that you want to keep in mind when you're doing function composition is that you really have kind of two steps involved, right? You start with a number x, so you kind of have, let's think of it as like three copies of the number line, right? And so there's one here, there's one here, there's one here, and you start with some point on one number line. That's your x, and you apply the first function to it. So you apply the function f, and f takes that value x, it takes that number x, and it assigns it to a new number. That new number is u. Okay, so somewhere here we have u, and of course u is the same thing as f of x, right? So f of x equals u. And then you're going to apply another function. So there's a function going between the first two copies of the real line, between copies 1 and 2, right? So f goes from copy 1 to copy 2, and then g goes from copy 2 to copy 3. So now there's a new function g, taking this value u and landing it on this third copy of the real line and getting you some value y. So what is y? Well, y is what you get when you take this number u and you plug it into g, right? But u was equal to f of x, so this is g of f of x. And so I guess I've done g composed with f rather than f composed with g, and keep in mind that does matter, right? If I do f first and then g, that's a different result than if I do g first and then f. So this is something to keep in mind. But so you do want to think of this sort of two-step process for function composition. You'll find that this does come in handy when you want to try to understand the chain rule. So before we state the chain rule, let's try to think about what's going on. If we sort of take this same thing and we think about what happens when we change our values a little bit, right? Now, here's kind of a very lazy way of writing down the definition of the derivative, right? It's the limiting value of these slopes, change in y over change in x, these slopes of these secant lines, as you let delta x go to 0, right? So delta x here is really just this h, and your delta y is the f of x plus h minus f of x as usual. And so one way to think about the limiting value, right, is so as delta x gets closer and closer to 0, as h gets closer and closer to 0, this ratio delta y over delta x gets closer and closer to the actual limiting value of the derivative. So for small values, right, for small enough values of h, this x minus a, the change in y is approximately given by taking the change in x and multiplying by the derivative. So the way you can kind of think of this in terms of these maps going from one copy to the other is, so let's say we're here, okay, and I've got my point A, and I've got my x over here, right? So here's my x, and so x is the same thing as a plus h. And so there's this gap here, right? So there's this gap between them, between a and x, and that's our delta x. Okay? And now I'm going to apply my function. So I have my function going between these two copies of the real line. So I apply my function, right? And so f is going to take this point. Here's my function f. And a is going to land over here at f of a. And x is going to land over here, okay, at f of x. And let's think of this is my x copy of the real line. I'm still going to keep this intermediate variable u in here. So so let's use u rather than y because I want to bring a second function into the picture here, right? So this gap here is my delta u, right? And so what we said above is that this delta u here, well, that's approximately f prime at a times delta x, okay? All right, so we've got that, and now let's give this f of a value. So this is going to be, let's call that b, and this is my u. Okay, and now I'm going to apply a second function. I'm going to apply a function g. So and that's going to take me over to my my y variables. So here's my y variables. So g is going to take this point and it's going to send it over to some point here. Okay, and what is this point going to be? This point is going to be g of b. Let's call that c. Okay, and it's going to take this point and it's going to land it somewhere over here. So let's say that's g of u, and that's my y, right? So what you want to do here is you want to think of, so this f prime, right? One way to think of this f prime in this equation is this is sort of a stretch factor, right? So you've got this little gap here, this delta x, right? You've got this gap of a certain size. You apply your function, and so the change in y is going to, it's the size of the, or sorry, change in u, this delta u, right, is going to be either a stretch or a shrink relative to the size of delta x, depending on the value of this f prime, right? But then the same thing happens when you apply this function g, right? We get a delta y here. And we can do the same sort of reasoning. Delta y is approximately, and let's just look at the second half of the graph here. So let's just look at this part here. Ignore the first part. Forget about f for a second. Delta y is what? It's going to be the value of the derivative of g at this starting point. Here's our starting point. We call that b. Okay? G prime at b times delta u, because we came from the u variables, we went to the y variables. Okay? But now let's plug things in. What is b? Now let's bring f into the picture. We bring our function f into the picture. What is b? b is f of a. What is delta u? Delta u is f prime of a times delta x. Right? So notice how we get a product of the two derivatives. We get so the overall change, the ratio between delta y and delta x, and maybe we should have done u's up here. Let's say that's a u, just to avoid confusion. So our ratio, our delta y over delta x ratio here, right, is approximately g prime at b times f prime at a. Right? It's just the product of the derivatives. So the chain rule, it seems like what we should be having here is something that relates the derivative of the big function, because we could also do this, right? We could go all the way from a straight to c using the composition, using g composed with f. And the same thing here, we can go from x all the way to y, right? So that should be somehow, this ratio should be related to the derivative of this composite, right? So the derivative of this composition should just be the product of the derivatives of the two functions that go into that composition. But just be careful, note that they're evaluated at different points, right? The outside function has to be evaluated at the inside function. So this is one thing to keep in mind. But essentially this is what the chain rule says, right? When you have this multi-step process and you have rates of change in each step of the process, then those rates multiply. In the textbook there's a nice illustration using gear wheels that kind of gets to this idea that if you have multiple things turning and they have different ratios, you multiply those ratios to get the overall gear ratio. This is the chain rule in action. All right, so here's the statement. We're going to make the formal statement now. Again, I've swapped the roles of f and g here, but so the chain rule says that if I start with two differentiable functions and I compose them, then the composition is going to be differentiable. And the way I calculate the derivative is I take the derivative of the outside function, right? So what we have is, so notice what we get here. It's the derivative of the outside, okay, but evaluated at the inside, and then we multiply by the derivative of the inside, right? So we need that product of two derivatives. The two most common mistakes that people make with the chain rule, one is probably just forgetting that second derivative altogether. That's probably the most common mistake. The second most common mistake is you'll find some people who take this derivative and they put it inside here. Rather than having g of a inside, you'll see f prime evaluated at g prime. But that's not what we want. So it's not a matter of, so when we're taking the derivative, kind of if we want to combine notations here, right? So the derivative of f of g of x. Some people have a temptation to just stick a prime on both of these and say that's the derivative. But that doesn't work. You need this product structure for the chain rule, right? So it's going to be the derivative of the first one evaluated at the inside, and then you have to multiply by the derivative of the inside. That's what the chain rule says. So let's look at an example. Okay. Here's a couple of functions. Now, one of the things that you might find useful here is you might find it useful to introduce an intermediate variable. So we might say, so if this is y, right, so we might be able to say it like this: y equals u cubed, where u is 2x cubed plus 4x squared. Okay? And so if we do it that way and we use the Leibniz notation, then dy dx, so the Leibniz notation says that should be dy du times du dx. Okay? So the derivative of y with respect to u, well, that's simple enough, right? Y is equal to u cubed. That's simply power rule. The derivative of u cubed is 3u squared. And then we have to multiply by the derivative of u with respect to x. So here's u. There are two terms. Both of them are power rule derivatives, right? So the derivative of x cubed is 3x squared times 2 gives me 6x squared. And then the derivative of x squared is 2x times 4 gives me 8x. You don't want to stop here though. You started with a function of x. Your final answer should be in terms of x. So we introduced this intermediate variable u, but we don't want to keep it around. We want to get rid of it. So let's write u back in terms of x. So u was 2x cubed plus 4x squared times, and oh, don't forget that square there, and then we multiply by the derivative of the inside. Okay? So you'll notice the pattern. It's the derivative of the outside function, the cube function, but then you have to evaluate it the inside function. Then you multiply by the derivative of the inside. Okay? So for this next one, now the next one is a little bit trickier because actually there are three functions being composed here. Okay? You've got the fifth power being plugged into the sine function, which is being plugged into a squaring function. And so we've got to really break things down here. And when you're composing three or more functions, the same thing works. You just you split things up. So we could think of this as, if this is my y, so y is equal to u squared, where u is equal to sine of, I need one more letter, let's go with v, and v is x to the fifth. And so when I have three functions like this, my dy dx is going to be, I take the derivative of y with respect to u, right? Y is written in terms of u, and then u is written in terms of v, so I do du dv, and then v is written in terms of x, so I get dv dx. So the derivative of u squared is 2u, the derivative of sine v is cos v, the derivative of x to the fifth is 5x to the fourth, but again we don't want to leave it like that. We got to get rid of these intermediate variables. So what was u? U is sine v, but v is x to the fifth. So 2 sine x to the fifth times cos x to the fifth times 5x to the fourth, and you've got your derivative. Okay, we'll stop here, and in the next video we're going to look at a few more examples involving the chain rule.